This lecture is about causal research in marketing, and I'll be limiting most of my comments to experiments. As with other research designs, experiments are uh, threatened by error, and that error can be either random or systematic. Random error, I've mentioned before, for experiments, the biggest component of random error is individual differences. That is, age, knowledge, IQ, personality, mood, differences among the people. All these things can be influential, can have an effect on the dependent variable, and by chance, one might have two experimental conditions that varied dramatically on individual differences, and thus we would see a difference in the dependent measures that was due simply to random error. Another random error is changes in experimental conditions that occur randomly. Now, if one were assessing two different versions of an ad, for example, and the ad was presented via a slide or an image on an internet, on a computer screen, it's very unlikely that there would be random changes in the ad. But if we were doing the experiment on salesperson expertise, Joe's presentation would differ each time he did it. There would be random differences. Sometimes Joe would be in a good mood, sometimes he'd be in a bad mood, sometimes he would be more fluent than others, sometimes he would be friendlier than others. And those differences, to a certain extent, could be systematic. It could be that, for example, Joe gets more comfortable over time. But even if we had him do the presentation many, many times before the experiment so that he was essentially as fluent as he would ever be, there would be random differences simply because humans are complicated and they can't perform exactly the same way all the time. And then getting back to the ads, even though the ad stimulus is exactly the same, the situation in which it's presented will vary. There'll be slightly different ambient factors, temperature, noise level. Even in a fairly controlled laboratory situation, there'll be small differences from one time to the next. Systematic errors, very similar to with surveys, sample bias. If there may be, of course, random differences between the samples that you can't control for, but there may be systematic biases that should be controlled for. If you have a two-condition experiment, if one has a two-condition experiment, one must be very careful to randomly assign people. It is not appropriate to fill the first condition with the first 50 volunteers and fill the second condition with the second 50 volunteers. Obviously, that introduces a potential bias based on promptness or interest in the study or willingness to volunteer. Likewise, if I were to run an experiment in class and put the first two rows in one condition and the back two rows in another condition, there'd be the possibility that I had differences in hearing ability or in visual acuity or in interest in the class. The other systematic error is confounds. A confound is literally the finding together of two factors. So if a manipulation introduces more than one level of the independent variable, But if it simultaneously introduces more than one level of another factor, that other factor may represent a systematic bias. In the research I'm going to present, we manipulated whether or not a coffee was branded as fair trade, and we had a short explanation of what fair trade meant. Well, it's possible that one could construct a definition of fair trade that required a couple of sentences explanation, and that might be contrasted with another coffee that was not labeled as fair trade and so would not have any explanation. So the two would differ in that one was fair trade and one was not, but they'd also differ in that one had more information, more words, more text than the other. So if the manipulations are in the form of an advertisement, you'd have one that was low in text and one that was high in text. And it may be that simply having more text causes an effect. So experimenters need to be careful to try to eliminate or control for confounding variables. Well, how do experiments control for alternative explanations? The most important way to control is through random assignment, because random assignment controls for all of the individual differences that might explain differences. It prevents one from saying, well, this result was due to having mostly people who like the brand in one condition and mostly people who didn't like the brand in another condition, or mostly people who are aware of the brand in one condition and mostly people who are unaware in the other condition, or mostly older people and mostly younger people. Random assignment assures that that does not happen. Second, standardization of procedures. Ideally, exactly the same thing happens in each condition except the level of the independent variable. And some experiments go so far as to have to eliminate the human element, because as I said earlier, humans will vary randomly from time to time. So instructions will be recorded. All the presentations will be mechanical. That's not often possible. If it's not, the experimenter has to be very careful to try to minimize any potential differences. So random assignment is important, but if the experimenter knows that there are certain variables that need to be controlled, he controls by sample management. Sample management can be done two ways. One is to match on the levels of certain variables. So if one knows ahead of time that age is going to be important, he can design the sample so that the same age distribution occurs in both samples. And the second is statistical control. If a sample can't be matched, at least those variables can be measured, and then those measures can be introduced as covariance. Essentially, their effects can be eliminated statistically before examining the relationship between the independent and dependent variables. Some experimental designs have more control than others. For example, we'll talk about these later, but for example, the least control occurs in a one case design, where a case study, for example, where one is simply looking at what happens in one instance. There's no control. There's no sense of what the measures were before something happened. We only have the case, what happened and what happened afterwards. And finally, there's a trade-off when one is trying to introduce controls. The amount of information versus statistical power. As one introduces control variables, essentially what one is doing is creating subcategories. So if, for example, one expects that sex is going to play a role, and one wants to include both males and females and measure sex so that those can be that effect can be eliminated, then one is creating two subsamples, and each of them has only half of the total size of the sample, which reduces statistical power. So there may be a case where lots and lots of variables are potentially need control, but there isn't enough budget to get a large enough sample to control for all of them. How are experiments interpreted? Well, the overriding goal of experiments is an inference of causation. So the aim of the interpretation is, can or do the results support an interpretation that the independent variable caused a change in the dependent variable? Most experiments have more than one independent variable. And if that's the case, the experimenter must look at both main effects and interaction effects. A main effect occurs when different levels of one independent variable have overall different effects on the dependent variable. An interaction effect occurs when different levels of one independent variable have different have effects on the dependent variable depending on the level of another independent variable. So for example, if we were looking at the expertise of salesperson on the success of the sales call, we might find that experts were better than inexperts if the product were complex, but not if the product were simple. So that would be an interaction effect where you would see an improvement in sales success for complex products, but you'd see essentially no effect for simple products. And when there's an interaction, it must be broken down. It can be misleading to interpret the main effect, or it's simply incomplete to interpret the main effect. For that example, you might see that there's a slightly better success rate for experts, but you wouldn't want to conclude that in general experts are better than inexperts. You'd like to know that there's this moderating effect of product complexity. Alternative explanations are other competing inferences from the results. Alternative explanations are sometimes called rival hypotheses. I guess that term, rival hypotheses, makes more sense whenever the other explanation involves concepts. If the other explanation is simply some sort of error component, then it would just be an alternative explanation. So these alternative explanations threaten the inference of causation, and researchers need to be skeptical looking at research results, always looking for alternative explanations. Remember that an alternative explanation is not an alternative explanation if you simply criticize the research design. An alternative explanation accounts for the results. So it simultaneously criticizes the design and explains the data that came from that design. Replications are often necessary in experimental research. They're not necessary typically. Well, there are two reasons, I guess. One is to increase the confidence of the inference of causation, to assure that it wasn't due to chance. or to assure that it wasn't due to some idiosyncratic characteristic of the experiment. But more generally for marketing, it's to demonstrate the robustness of the effect. So it has more to do with the ability to generalize the effects to other situations. So often research, for example, will be done in an academic setting, in a controlled, sterile environment with a homogeneous group of people, for example, students. And in order to make it useful for marketers, it needs to be replicated in something that's more like the marketplace.